Hello everyone, welcome to CSCN 1001 Computer and Network Security. This is Dr. Amr Al-Mogi. I'd like to welcome you to this lecture first of all. Up to last lecture we have been discussing symmetric encryption in details. We have discussed the most prevalent symmetric encryption algorithm that is out there now in use, which is AES. We have discussed modes of encryption. And we also discussed pseudo-random numbers and their use in stream ciphers as well. Starting this lecture, we are going to go into a new topic, which is public key cryptography. And we are going to stay with this topic for 2 or 3 lectures because public key cryptography is a branch of cryptography that has extended use and is quite different from what we have studied so far. Okay. So in this lecture, we are going to revise our introduction into public key cryptography, and we want to understand its basics, and we want to understand its applications and the differences between public key cryptography and symmetric cryptography or symmetric encryption. Then we are going to go into our first public key cryptography algorithm, which is RSA. We are going to understand how it works, and we are going to understand its mathematical foundations by looking at its mathematical proof. And by the end of this lecture, you should be able to solve problems related to encryption and decryption using RSA. Just a heads up, before we start anything, this lecture has heavy mathematical proofs, and so you should be prepared for that. Get out a pen and paper, make sure that you are focused, make sure that this is a good time for you to watch this video. And while we are explaining the mathematical concepts, I want you to pause the video repeatedly and repeat these mathematical steps after me and make sure you understand them fully. Okay, so in symmetric cryptography, we said that encryption and decryption are done using the same key. So you encrypt the plain text with the key, and the key is shared between the sender and the receiver, even though the sharing of the key itself is not part of the encryption algorithm. But if you want to decrypt the ciphertext to obtain the original plain text, you have to decrypt using the exact same key. Okay? In public key cryptography, there are actually 2 keys. Every user in the system has a pair of keys, and the pair are related by a mathematical equation. Okay, one of those keys is called the public key, and it is published. It is available at a registry or something like that for anyone to actually see and anyone to use. And its pair is called the private key, and this one is not shared with anyone other than its owner. So only the owner knows the private key. Okay. Why is it called asymmetric encryption? Because if you encrypt with one key, you can only decrypt with the other key. So if you encrypt with the public key, you can only decrypt with its pair key, which is the private key. Okay, so you encrypt and decrypt with the different keys, which is why we call it asymmetric encryption or public key cryptography in this case. Okay, now up to the 1970s, symmetric encryption was actually the only branch of cryptography that was in wide use, and public key cryptography was not actually invented for the sake of regular encryption like AES. Public key cryptography was invented to address 2 key issues. The first one is key distribution. How do we basically exchange this symmetric key in AES? Okay, before the invention of public key cryptography, we had to rely on what is called a key distribution system, and there had to be a centralized node in the system or a centralized server that is responsible for distributing keys to everyone who needs them. And so by default, you had to trust this centralized server, and this centralized server became a very attractive point of attack. It's also a single point of failure, so it had a lot of problems. So it would be desirable that any 2 parties that wish to communicate secretly can exchange the symmetric key also secretly and start encrypting their data using this shared key. Okay, this is, for example, what you do when you access a server on the web. If you're using HTTPS, then you're having actually an encrypted communication session between you and that server. And there is no centralized node that would give you those symmetric keys or secret keys for you to do your encryption. you actually exchange the secret key between you and the server using an algorithm that is called Diffie-Hellman algorithm. We'll actually discuss it in details probably in the next lecture. But this is actually the algorithm that allows two parties to exchange a key with each other securely without actually involving a third party. So this was one of the key motivations for public key cryptography. The second key issue is digital signatures. A digital signature is, by its name or from its name, is a way to digitize a signature. When you sign a piece of paper just by hand signature, you are basically verifying your identity. You're saying, I am the only one who could have signed this document. I am the only one who knows this signature. Okay? They wanted basically a digital version of that. You want to basically authenticate a message. You want to say, I am the only one who could have generated this message. Then you want to digitally sign it. By having a digital signature, they were able actually to enable a very wide variety of applications and a very wide variety of transactions on the internet securely between people who do not have to trust each other. The first public key cryptography algorithm that was invented by Whitfield Diffie and Martin Hellman, and it is actually called the Diffie-Hellman algorithm at Stanford University in 1976. In these two figures, we see actually the two main uses for public key cryptography, and we actually discussed them before, so I will just be going over them briefly. If you want to do regular encryption, you just want to send a message such that you achieve the security objective of confidentiality. So every user in the system, as we said, has a pair of keys, public key and the private key. So Alice will have the public key of Alice and the private key of Alice, and these two keys are bounded by a mathematical relationship. That means they're not just two random keys, they are a pair of keys that are bound by a mathematical relationship. Okay? If you have Bob in the system, then Bob will also have a different pair of keys, public key of Bob and the private key of Bob. So Bob and Alice will each publish their public key, and they will keep their private key secret. That means they will not share it with anyone, even with each other, even if they trust each other, because there is no need. So if Alice wants to send a confidential message to Bob, okay, basically what this means is that Alice wants to send a message such that only Bob will be able to read it, which means that only Bob will be able to decrypt it. If only Bob would be able to decrypt it, then Bob would have to decrypt with the key that only he owns. And this key is actually the private key. There is no other key that is owned only by Bob. And so for this case, Bob has to decrypt using his private key. Okay. So if I want Bob to decrypt using his private key, what should I encrypt the message with? We said that in order for you to decrypt, you have to use the partner key for the key that was used in the encryption. So if I want to decrypt with the private key of Bob, then I have to encrypt with the public key of Bob. Okay. Notice here that Alice encrypts with the public key, not of herself. Alice encrypts with the public key of Bob. How does Alice know the public key of Bob? Because it's the public key. It's public. Everyone knows it. Bob actually publishes it. Anyone can have it and anyone can read it. Okay? So, if Alice encrypts with the public key of Bob, then only Bob will be able to decrypt using his private key, and you have achieved confidentiality in this case. Now, if I want to achieve the security objective of authentication, that means I want to send a message. So Alice wants to send a message to Bob such that this message is authenticated, meaning that Bob would be able to verify that Alice was the one who sent the message. Okay? So if I want to authenticate Alice, I have to encrypt with a key that only Alice has, so that Bob would know that the message must have been encrypted with a key that only Alice has. There is no other key that only Alice has except the private key of Alice. Okay. So if I want to authenticate a message, I encrypt it with the private key of the user. Now, how would Bob verify? Bob would receive this encrypted message using the private key of Alice, and so Bob can now decrypt using the public key of Alice. Now, note here two things. First of all, Bob is able to verify or authenticate the message coming from Alice without having access to the private key of Alice. So the private key of Alice is still kept secret at Alice's station. Alice doesn't have to share it with anyone. Alice can indeed encrypt with it, such that everyone is able to decrypt with her partner key or her public key, such that they are able to authenticate the message that it is indeed coming from Alice. This is a very important feature, and this is indeed a digital signature. It is as if Alice has digitally signed her message. Okay? Another thing to note here is that in this example, Alice has encrypted with her own private key to achieve authentication, whereas in the first example, Alice encrypted with the public key of Bob. So if I want to achieve confidentiality, I encrypt with the public key of the receiver. Okay? If I want to achieve authentication, I encrypt with the private key of the sender. Okay? All right. This here achieves authentication, achieves also the objective of non-repudiation. And non-repudiation here means that Alice would not be able to deny sending the message because no one else, not even Bob, has access to her private key. This is actually a unique property of public key cryptography. Only public key cryptography has this property. Symmetric key cryptography doesn't have it because the key is shared between the sender and the receiver. And so in symmetric cryptography, the receiver can generate a message and claim that it came from the sender because the sender also has the key. Whereas in public key cryptography, only Alice has the private key. So if she encrypts with the private key, she must have been the one who generated the message. Okay, so this is how we achieve the objective of non-repudiation. But a very important note here that if Alice encrypts with her own private key, this message is open to the public. Anyone can decrypt and read because anyone can obtain Alice's public key. That means this is not a confidential message. It is an authenticated message or a digitally signed message. Okay. So someone might ask, why would you want to generate such a message? Well, basically systems have different uses. For example, think of a case where the management of a network, for example, wants to publish an announcement. So they want this announcement to be public, obviously. They want everyone to be able to read it, but they want everyone to know that it did indeed come from the management. So they want to digitally sign it, but they want it actually to be public. So this is an example where they would have to encrypt the message with their own private key. Okay. Different applications have different requirements and different properties, and so this serves one of these requirements or properties. Okay, so it is asymmetric because if you encrypt with a public key, you can only decrypt with the private key. What if you want to have both objectives? What if you want to achieve confidentiality and authentication as well? If you are using public key cryptography, then you would have to do two stages of encryption. First of all, the source will encrypt with his or her own private key. So you pass the message to the encryption algorithm together with the private key. Out comes a digitally signed message. You will encrypt it again with the public key of the receiver. So the message is actually encrypted twice. Once with the private key of the sender, private key of Alice, and another time with the public key of the receiver, which is the public key of Bob. Okay? And then you send the encrypted message. This is then your ciphertext. If the receiver wishes to decrypt, he has to do the same steps but in opposite order. So the last encryption step was at the encryption with the public key of Bob. And so Bob will have to start by decrypting with his own private key. And then out comes a message that has to be decrypted with Alice's public key. So Alice's public key is public. Bob will have access to it. They can decrypt and obtain the plain text back. Okay. Now, it is very important to note that public key cryptography is not a replacement for symmetric encryption. So even though public key cryptography is the newer form of encryption, and it has different properties, and it can indeed support regular encryption, it is not a replacement. We will see a little bit later that in order for public key cryptography algorithms to work, most of them have to rely on key sizes that are very large, much larger than AES. In AES, we saw that the maximum key size was actually 256 bits. In an algorithm such as RSA, in order for it to be secure by modern standards, the key size or the key size has to be on the order of 2048 bits. This much larger key size lead to the fact that public key algorithms are often much slower than symmetric encryption. And so symmetric encryption is still used for regular encryption. It's just that it is now complemented with public key cryptography. Generally speaking, we use public key cryptography to do authentication, to do digital signatures, to do key exchange, as we will see in the next lecture. But regular encryption still remains the field of AES and symmetric cryptography. It doesn't mean that you cannot do regular encryption with public key cryptography. You can. It's just that it is usually much slower. So these are the main three applications that we will take a look into in public key cryptography: regular encryption and decryption, digital signatures, and key exchange. The interesting thing is that algorithms for public key cryptography are quite often not used or cannot be used for all three applications. For example, RSA is a general purpose application. You can use it for encryption, decryption. You can use it for a digital signature by encrypting with the private key, and you can use it for key exchange as well. Whereas an algorithm such as the Diffie-Hellman algorithm can only be used for key exchange. You cannot actually use it to do anything else, as we will see in the next lecture. Similarly, the digital signature standard can only be used to generate digital signatures, cannot be used to generate a key, cannot be used for regular encryption. So some public key cryptography algorithms are proposed for a specific application only. The newest member of public key cryptography algorithms is a branch that is called elliptic curve cryptography. It does actually the same thing as public key cryptography algorithms, except that it needs a smaller key size to achieve the same security level. Okay, that's why it's becoming much more popular. It is used in many applications such as Tor. I think HTTPS also supports it, and so it is becoming indeed much more popular. Okay. So when we were discussing symmetric encryption, we discussed first its requirements. What do we require for having a good symmetric encryption algorithm? And we said that obviously it has to be secure against brute force attacks and cryptanalytic attacks. But the algorithm itself should be public. So there is no requirement that the algorithm be kept secret. We have actually the same exact requirement for public key cryptography. The algorithms are public. We know them. We know exactly how they work. Otherwise, we will not be able to actually trust how these algorithms should work. Okay. The other requirement is that it should be easy to encrypt and decrypt if you know the correct keys. But it should be computationally difficult to break the algorithm if you do not know the right key. So y equal f of k, f of x given the key k is easy if k and x are known. This is actually encryption. Okay, x is equal to f of y or f of negative 1 of y with the key k is also easy if k and y are known. So encrypting and decrypting are actually known. However, the same decryption should be infeasible if y is known but k is not known. That means if you don't know the key, it should be computationally difficult to break the algorithm and obtain back the plain text. One interesting thing about public key cryptography is that all algorithms rely on some kind of mathematical equation, some kind of mathematical concept, and typically they rely on modular arithmetic and number theory, as we will see in a little bit. Before we go into that, we will take a look at a couple of important applications of public key cryptography to see actually why it is different and why it is an important branch of cryptography algorithms. One of the most important applications of public key cryptography is what is known as public key certificates. When you access a website and you're using HTTPS, there is a way for the server to give you something called a security certificate, and the goal of the security certificate is for the server to identify its identity for you. Basically, the server authenticates itself to you. How does the server actually do that? Before the server can do that, the server has to go, or obviously the owners of this website, they have to go and purchase something called a security certificate. And they purchase the security certificate from a trusted authority. Okay? That is called the certificate authority, or CA. This certificate authority can be, for example, a bank, can be a government entity, can be an organization responsible for issuing these public key certificates. It's just a trusted authority. And so you give your credentials to this trusted authority. You tell it, my website is so and so. Here is actually what verifies my identity. And please give me a certificate that I can present to my users. And so the certificate authority will generate a certificate that includes all the information of the website or of the server, and will then proceed to generate a digital signature of the certificate. It is as if the certificate authority produces the certificate and digitally signs it. Okay, how do they produce this digital signature? They take the certificate and they pass it through something called a hash algorithm. We will study hash algorithms in details in, I think, 2 lectures, but the purpose of hash algorithms is to actually produce a digest of the message. They take the message and they produce a fixed size message that is much smaller than the original message. It is as if you have passed the message into a paper shredder. I'm sure you have seen it before. You have a paper, you pass it through a paper shredder, out comes shreds. These shreds, you can actually bulk them together. They have a smaller size than the original piece of paper, or they occupy a smaller space than the original piece of paper. And the shreds depend on the original message. The hash does the same thing. You take the message, you pass it through the hash, out comes a small message that has a fixed size, irrelevant actually of the original size of the message, as we will see how later. And its content, or the content of the hash, is a function of the content of the original message. Okay, so the certificate authority will generate the hash of the message and then will digitally sign the hash. That means they will encrypt the hash with the private key of the certificate authority. Why do we encrypt the hash rather than encrypt the original message? Because as we will see later, it is difficult to have another certificate that has the same hash. We will see actually that signing the hash or producing the hash is the way to achieve the integrity of the message, meaning that no one can actually change its content. Okay? So now you have a digitally signed hash. The certificate authority will then give the website the certificate as well as the digitally signed hash. They will concatenate them together and give this to the website. Now, when you as a user visit the website and you want to authenticate its identity, the website will simply give you the certificate with the digitally signed hash and will tell you, please take this information and see if you can verify. As a user, the way you will verify it is that you will actually repeat the steps. You will take the certificate, okay? You will take the certificate and you will pass it to the hash algorithm. The hash algorithm will be a public algorithm that everyone knows it, and it doesn't take a key or anything. It just works. So you take the certificate and you pass it through the hash, and then out comes the digest of the message or the digest of the certificate. And then you will take the digitally signed hash that the website gave to you that was passed to the website from the certificate authority, and you will decrypt it using the public key of the certificate authority, which is obviously public. You will obtain a decrypted message. If these two match, then the digitally signed digest must have been produced by the certificate authority, because I was able to decrypt it with the public key of the certificate authority, which means that it must have been encrypted only with the private key of the certificate authority. So now I have verified the digital signature. So again, the certificate authority issues the certificate, it hashes the certificate, and digitally signs the hash. It encrypts the hash with the private key of the certificate authority and gives the certificate along with the digitally signed hash to the website. When you, as a user, wish to verify that, You take the certificate from the website and you pass it through the hash. You produce the message digest. You take the digitally signed hash also from the certificate, also from the website, and this digitally signed hash has been given to the website from the certificate authority. You decrypt this digitally signed hash using the public key of the certificate authority, and you match or you compare this decrypted hash with the hash that you produced from the certificate that was given to you from the website. If they match, then the message is, or the certificate is authenticated. Now note here that you are able to actually authenticate the identity of the website without going back to the certificate authority. The certificate authority is contacted once. Only the website contacts the certificate authority to obtain a digitally signed certificate, and that's it. Once you want to verify the identity of the website, they give you the certificate and the digitally signed hash, and this is actually enough. Okay. This is an example of a certificate. You can actually view the certificate of any website on your computer. It has some information. We will see actually this information in details when we discuss security certificates. It has the name of the organization. It has the serial number of the certificate itself. It has the issuer. Basically, the issuer is the certificate authority who issued the security certificate. It also has the name of the website or the organization to which the certificate is issued, and it has the validity information. When will it expire? And then it has the public key of the website. Okay, so that when you communicate with the website, you will actually be able to validate that this is the correct public key. The figure on the right shows you a fake certificate. So it is a fake digital signature. Then it is something that can actually be easily verified because the digital signature will not match the digital signature of an original certificate authority or an authentic certificate authority. The second application of public key cryptography that we will discuss is called the digital envelope. Now imagine that you want to send a message to any destination or any receiver, but you don't have a shared key in common with that receiver. Public key cryptography solves this problem. So you take the message and you encrypt it with a symmetric key. For example, you encrypt it using AS using a key. Now, in order for the receiver to decrypt, you have to give them this key. As we said, you have not actually exchanged a key with them before. So how do you give them this key securely? You can actually take the key and encrypt it with the public key of the receiver. Okay. Obviously, the public key of the receiver is public. Anyone knows it. So you can encrypt the key with the public key of the receiver. And then you send the encrypted key along with the encrypted message. So both of them are now encrypted. Anyone who sees them will not be able to break them. And this is the nice thing about encryption. It is not hidden. It is not as if you are hiding the fact that you're sending information to someone. You're sending it in plain sight, but it is encrypted so that anyone who is eavesdropping will not actually be able to understand. This is called a digital envelope. How will the receiver actually obtain the message? The receiver will open the message, will find the encrypted key, and we will be able to decrypt it using the private key of the receiver. Okay? And then, after obtaining the symmetric key, the receiver can decrypt the message using the symmetric key and obtain the plain text back. So you may ask, why do I need to actually have a symmetric key and the public key? Why can't I just encrypt the entire message with the receiver public key from the start? Well, we have covered this before. It's because symmetric encryption is faster than public key cryptography. So in this case, you're only encrypting a small piece of information, which is the key, but the bulk of the message, which is expected to be much larger in size, is encrypted using symmetric cryptography, which is faster. Okay. So public key cryptography also has some security requirements. So a public key cryptography algorithm also has to be immune against brute force attacks, but typically this is not a problem in public key cryptography because, as we said, the size of the key in public key cryptography algorithms is typically very large. So RSA, we're talking about 2048 bits. So in this case, brute force is nearly impossible. Actually, attackers of public key cryptography do not even aim or do not even try for brute force. Instead, there are mathematical attacks, there are mathematical problems that attackers try to exploit in order to break public key cryptography algorithms. What we will see actually when we study public key cryptography algorithms is that the problem or the way to break the algorithm is typically known to everyone. For example, in RSA, as we will see in a little bit, there is something called the factorization attack. Everyone knows it. I will actually explain it to you. But if you choose the numbers for the algorithm in a right way, and if you choose them to be large enough, this attack will be very, very difficult or infeasible to execute. This is actually the security of public key cryptography. Okay, now we can start to look into the first public key cryptography algorithm, and hopefully this will clarify a lot of concepts that we have been explaining. First thing we have to say is that math is cool, because all public key cryptography algorithms rely one way or the other on some form of math. And particularly the algorithms that we will discuss rely on modular arithmetic. Okay, so if Alice has 15 apples, she wishes to distribute them evenly over 6 friends. We know that there will be a remainder, and we find this remainder using modular arithmetic. This is just the way to calculate mod if your calculator doesn't calculate it right away. So now, RSA was one of the earlier cryptography, public key cryptography algorithms that were invented. They were invented it was invented in 1977 by 3 scientists known as Rivest, Shamir, and Edelman. This is where the abbreviation RSA actually comes from. And the security of RSA comes from the cost of factoring large numbers. This is something that we will see. And so, to take a look at RSA, before we see how you can actually encrypt with RSA, we will have to see how to set up or how to prepare the environment of RSA. So in public key cryptography, we said that every user has a pair of keys. It's the public key and the private key. And there is a mathematical relationship that binds the public key with the private key. This is what we will actually start with, the key setup. So before you can actually encrypt and decrypt using RSA, you have to generate the pair of keys. You have to generate the public key and the private key. To do that, you have to first agree on a set of parameters. So every user, if RSA is being used by 10 users, they have to agree first on a set of parameters. They have to agree on 2 prime numbers, P and Q, where the product n is the multiplication or the product of P and Q. So the system modulus n has to be the product of 2 prime numbers. Any 2 prime numbers would work, but obviously for the algorithm to be secure, you have to choose P and Q as very large prime number, and by very large, I mean on the order of 1024 or 2048 bits. Okay. If n is equal to P and Q, there is something called the Euler totient, which I'm going to discuss in the next slide. Phi n is equal to P minus 1 multiplied by Q minus 1. Once you agree on P and Q and calculate n, you will be able to select now the public key. The public key or the encryption key E, okay, is chosen such that the greatest common divisor between E and phi n is equal to 1. So you can choose any public key E such that the greatest common divisor between E and phi n is equal to 1. So every user in the system will choose its own E, given that they already know n, given that they have all already agreed on P and Q, and therefore calculated n, and therefore calculated the Euler totient of n, which is phi n. Given that they calculated phi n, they will be able to choose their own public key E, such that the greatest common divisor between E and phi n is 1, and E has to be less than phi n. Okay. So now the public key is determined. It's actually E and N. So the public key is the combination of 2 numbers, E and N. So how does the user then calculate the private key? We said that the private key has a mathematical relationship that binds it with the public key, and this is actually the mathematical relationship. It is ED congruent to 1 mod phi n, or we can say ED mod phi n is equal to 1. Okay, this is actually the mathematical relationship. You have E, you have phi n, you can calculate D from it. And so the private key is D and N, and there is a mathematical relationship which binds the private key with the public key. D has to be less than N in this case. Okay? So again, the steps for key generation, you choose two prime numbers P and Q. And so now you can calculate the system modulus N, which is P multiplied by Q. You can also calculate the Euler totient of N, which is P minus 1 multiplied by Q minus 1. Given that, you can choose the public key, which is a number where the greatest common divisor of E and phi N is equal to 1, and E is less than phi N. The greatest common divisor, meaning that the largest number that divides E and phi N is 1. Okay? It means that they are relatively prime to each other. This is what we call it. Okay? So given that you chose E, you can actually use this equation, ED mod phi N is equal to 1, to figure out the value of D, which is the private key. And so now you have the private key and you have the public key. So as we said, if you want to encrypt, you encrypt with one key, you will have to decrypt with the other. And so now we can find, or we can look at the encryption and decryption messages, the encryption and decryption equations. If you want to encrypt a message M, okay, what you do is you raise its power to E, which is the public key of the receiver, obviously, if you want to send a confidential message. Okay, you raise its power to E and you do mod N. So the ciphertext is equal to M power E mod N, and M in this case has to be less than the value of N. So you can only encrypt up to the value of N. Okay, so this is the encrypted message. This is the ciphertext. How does the receiver decrypt? The receiver will take the ciphertext, will raise it to the power of their own private key, and do mod N. So the message M is equal to C power D mod N, and you have retrieved the plain text back. Okay, so if N must be less than the system modulus N, if M must be less than N, as we saw here, then if you are encrypting a large message, you can divide it into smaller blocks, as we saw in symmetric encryption. Okay, so how do you encrypt anything? How do you encrypt, for example, text? How do you encrypt an image? Well, if you are not encrypting integers, obviously all of this must be integers. If you are not encrypting integers, you have to code it. For example, if you want to encrypt letters, you have to encrypt their ASCII character equivalent, for example. If you want to encrypt an image, you can take, for example, a group of bits, you convert them to a decimal, you convert them to an integer value, and then you encrypt that integer value. Public key cryptography only encrypts integer value. Okay. Okay. At this point, before we go into anything else, before we even see an example of RSA, we will go into its mathematical proof. This part is a little bit challenging, and so I want you to follow closely, pause the video frequently, and make sure that you are following what we are saying. Before we go into the proof, there are some mathematical relationships that we have to be familiar with. First one is the concept of an Euler totient. The Euler totient phi n, we saw it in the key generation of RSA, is basically the number of positive integers less than n that are relatively prime to n. So phi of n is the number of positive integers less than n that are relatively prime to n. It means that it's the number of numbers, okay, less than n, where the greatest common divisor between any of these numbers and n is equal to 1. Okay, so obviously phi of 1 is equal to 1 because there is only one number that is relatively prime to n, which is n itself. Okay, if you want to calculate the Euler totient of 6, so phi of 6, okay, what are the numbers, or what are the positive numbers less than 6 that are relatively prime to 6? They are only 1 and 5. 2 is not relatively prime to 6, 3 is not relatively prime to 6, 4 is not relatively prime to 6, 5 is, and 1 is. So you only have two numbers, 1 and 5, that are less than n, that are relatively prime to n, which is 6. Okay, so in this case, phi of 6 is equal to 2 because there are only two numbers that are relatively prime to 6. Okay, what happens if n is a prime number? Okay, if you are calculating, for example, phi of 7. What are the numbers that are less than 7 that are relatively prime to 7? They are actually 1, 2, 3, 4, 5, and 6. All the numbers less than 7 are relatively prime to 7 because 7 is a prime number. For all prime numbers, all the numbers less than this prime number are relatively prime to it. And so we can say easily that phi of p is equal to p minus 1 if p is prime. So for all prime numbers, phi of p is equal to p minus 1. And this now leads us to phi of n. In RSA, we said that we have phi of n, where n is equal to p multiplied by q, and p and q are both prime numbers. So phi of n is the product of two prime numbers, which is equal to phi of p multiplied by phi of q, which is equal to p minus 1 multiplied by q minus 1. This is why phi of n is equal to p minus 1 multiplied by q minus 1. This is the first thing we will need for for the proof of RSA and for RSA itself, actually. Second thing we will need is something called Euler's theorem, which states that for any two integers a and n, such that a and n are relatively prime, that means the greatest common divisor between a and n is 1, we have this relationship a power phi n mod n is equal to 1, where a and n are relatively prime. Okay, Euler's theorem is very, very important for the proof of RSA. Last thing we will need is some properties of mod. If you have a mod n multiplied by b mod n all together mod n, this is equal to ab mod n. And if you have a mod n minus b mod n all together mod n, this is equal to a minus b mod n. Okay? Okay, now we are actually ready to go into the proof of RSA. We want to prove the following. We want to prove that if I raise m to the power of ed mod n, this is equal to m. Why is that? How do I decrypt? C is equal to m power e mod n, and m is equal to c power d mod n. So what is actually c? This is equal to m is equal to m power ed. Just replace c power d with m power e power d. Okay, m power d mod n. Okay. This is what we want to prove. Okay, we want to prove that for m less than n, when n is equal to pq is the product of two prime numbers, we have m power ed mod n is equal to m, if and only if e and d are chosen such that ed mod phi n is equal to 1. This can alternatively be written as ed equal k phi n plus 1. Why? Because when we say ed mod phi n is equal to 1, that means the remainder of the division of ed over phi n is equal to 1. The remainder of ed divided by phi n is equal to 1, which means that ed is equal to some integer k multiplied by phi n plus 1. Okay, so if you replace ed by k phi n plus 1 in the original equation, you get m power k phi n plus 1 mod n, okay, which is ed, which we know that phi n is equal to p minus 1 multiplied by q minus 1, so you replace them with that. You get m power k p minus 1 q minus 1 plus 1 mod n. We want to prove that this is equal to m. Okay. Now we go into the proof. We want to show the proof in two steps. Basically, we want to prove that this equation, which is in mod n is equal to m, we will do the proof by first doing it mod p, and then we will do the proof by for mod q, and then we will be able to prove that mod n is equal to m. So the first case that we have is that we have m power k p minus 1, okay, multiplied by q minus 1 plus 1 mod p. Okay, we want to prove that this is equal to m mod p. Okay, so that we are able to decrypt. We have two cases. Either m and p are relatively prime, or they're not. Okay, if m and p are relatively prime, that means that p divides m. So if m and p are relatively prime, it means that p divides m. In this case, m mod p is actually equal to 0. Okay, if P divides M, then M over P will have no remainder. That means M mod P is equal to 0, which means that M power K P minus 1 Q minus 1 plus 1 mod P is equal to 0. Why? Because if you have X mod N is equal to 1, then X squared mod N will also be equal to 1. That actually X power Y mod N will be equal to 1. If you have X mod N equal to 0, then X squared mod N will be equal to 0, and X power anything mod N will also be equal to 0. So if you have M mod P equal to 0, then M power anything mod P is also equal to 0. Okay. Then in this case, M power K P minus 1 Q minus 1 plus 1 is equal indeed to M mod P. Both of them are actually equal to 0. Okay. This is in case that M and P are relatively prime, are actually not relatively prime. Okay. If M and P are indeed relatively prime, so now we do the case M and P are relatively prime. That means that P does not actually divide M. Okay. If they are not relatively prime, if they are actually, sorry, relatively prime, then M phi P mod P is equal to 1. This is from Euler's theorem. If you remember Euler's theorem, we said that A power phi n mod n is equal to 1 if A and n are relatively prime, or the greatest common divisor between them is actually equal to 1. So in our first case, we assume that M and P are not relatively prime. That means their greatest common divisor is not 1. Okay, that means that M mod P is equal to 0, and we then showed that in this case, M Kp minus 1 Q minus 1 plus 1 is equal to M mod P is equal to 0. In our second case, we are assuming now that M and P are relatively prime. So now Euler's theorem is satisfied. So M phi P mod P is equal to 1. So now we can proceed. Now we can say M power K P minus 1 Q minus 1 plus 1 mod P. Remember, we're using mod P, not mod N, because we're going to do mod P, and we're going to then repeat the whole proof using mod N, and then we will be able to, we're going to do mod P and then mod Q, then we're able to do that it will stand for mod N. So if you have this equation, you can actually rewrite it as M multiplied by M, K, P minus 1, Q minus 1. Okay, just actually take the plus 1 and put it as an M by itself, and the whole thing is mod P. Okay, this is then equal to M multiplied by M P minus 1, all of that to the power K Q minus 1, okay, and all of that is mod P. This is then equal to M. Okay, M P minus 1 is actually M phi P, because phi P is equal to P minus 1 if P is prime, as we know. So this is M multiplied by M phi P. Just replace M to the power of P minus 1 by M phi P. Okay, and all of this to the power of K Q minus 1. And all of this is mod P. Okay, now what does this boil down to? Just actually use the properties of mod. This can be rewritten as M mod P multiplied by M phi P mod P, and just bring the power outside to be K Q minus 1. Okay. M mod phi, M power phi P mod P is actually, according to Euler's theorem, equal to 1. So this now boils down to m mod p multiplied by 1 to the power of k q minus 1. 1 to the power of anything is equal to 1, which now becomes m mod p. Okay? So now we have proved that whether m and p are relatively prime or m and p are not relatively prime, this value here, m power k p minus 1 q minus 1 plus 1 mod p is equal to m mod p. Now we can say that since these two values are equal to each other, we can actually say that m power k p minus 1 q minus 1 plus 1 mod p minus m mod p is equal to 0. Why? Because they're equal to each other. So just bring one to the left-hand side. This then will be equal to 0. So that means that P divides, uh, it actually means by the properties of mod that M K P minus 1 Q minus 1 plus 1 minus M everything mod P is equal to 0. Okay, that means that M divides, P divides this entire value. Okay, we can repeat the exact same proof for Q. So just actually go replace mod P with mod Q and do the exact same proof. You will find that it will stand because P, all we assumed is that P is a prime number. So we can do the exact same proof by saying that Q is a prime number. So now you have this value, okay, this value, P divides it and Q divides it as well by the same reasoning. That means that M power Kp minus 1 Q minus 1 plus 1 minus M mod P is equal to 0, and M Kp minus 1 Q minus 1 plus 1 minus M mod Q is equal to 0. So Q and M both divide this value. We can then say that M power K P minus 1 Q minus 1 plus 1 minus M is equal to a constant that is multiplied by P and Q. Why? Because both P and Q will divide it. That means there must be a constant R that is actually, if you multiply it by P and Q, you get actually the same value, which is NR. P multiplied by Q is just N. Okay? And finally, we can then say that N divides M K P minus 1 Q minus 1 plus 1 minus M. So P divides it, Q divides it, and so N divides it too, which means that, I'm just writing on the top because I ran out of space. It means that M power K phi N plus 1, M power N phi N plus 1 mod N is equal to M K P minus 1 Q minus 1 plus 1 mod N is equal to M. So now we have proven by actually doing the proof first for P and then doing the proof for Q that we are able now to prove that if you raise the power of M to the power of ED mod N, you will get actually the original message. You'll get the original message back. Okay, so if you, the goal of actually going through the RSA proof is to show you the deep mathematical concepts of RSA. You will not be asked to repeat the proof in the exam, but it's important to understand the mathematical concepts of RSA to appreciate actually the inner workings of this algorithm. The proof itself is available in the book Cryptography and Network Security, and it's in the appendix of the RSA chapter. Now we can actually go through an RSA example. So if you want to encrypt and decrypt with RSA, First thing we do is that we choose two prime numbers. Let's choose p equals 17 and q equals 11. These are just examples. Once we choose the two prime numbers, we can calculate the system modulus n, which is p multiplied by q, which is 17 multiplied by 11, which is 187. We can also compute the Euler totient, p minus 1 by q minus 1, which is 16 by 10, which is 160. Now that we have calculated the Euler totient, we can start to choose the public key. The public key is any value e, such that e and phi n, which is 160, their greatest common divisor is equal to 1. If we choose any prime number, this would be a safe choice actually. So e equals 7 satisfies this equation. And now we can calculate dE equal mod 160. We have e, we have phi n, which is 160. Now we can calculate d. D has to be less than phi n or 160. In this case, d has a unique value, which is 23. How to actually solve this equation, I will show you actually in a little bit the Euclidean algorithm. For now, actually, even trial and error, because these are small enough numbers, trial and error will actually lead you to the correct value of d. And now the public key is 7 and 187. The private key is 23 and 187. If we want to encrypt, let's say you want to encrypt a message m is equal to 88, you have to be sure that m is less than n. Okay, the ciphertext is equal to 88 power 7 mod 187, which is equal to 11. If you want to decrypt, you take 11, you raise it to the power of d, which is 23, mod n, which is 187, you get 88 back. Okay, so obviously it works. Now, if you want to raise the exponent of a number and the result is very large, to do it on your calculator. So if you do 88 power 7, this is actually too large on a calculator. There is an algorithm that is called the square and multiply. Basically, you start by calculating, for example, 88 power 1 or 88 power 2, and then do mod 87. And then you take that and you multiply by another 88, and you keep doing that until you actually get 88 power 7. This is because if you have a mod n multiplied by b mod n, all of this mod n, this is equal to ab mod n, as we explained before. So if you have, for example, 88 power 4 mod n multiplied by 88 power 3 mod n, okay, and all of this mod n, this is actually equal to 88 power 4 multiplied by 88 power 3 mod n. That's the basic idea. You calculate smaller powers and you use those to calculate higher powers, because the higher powers you'll not be able to put them on your calculator, and so you can put smaller powers, and if you do mod a small power, then the number itself gets reduced, and so you will be able to do the calculation this way. A key part of RSA is being able to choose large prime numbers. Okay, P and Q have to be prime numbers, and we said the larger the values of P and Q, the more secure the algorithm is. Unfortunately, there is no test for primality. There is no test that you will do that will tell you that this number is 100% prime. There are actually tests that show that the number is not prime. So usually what we do is that we run a number of these tests, and if they all fail, if they all show that the number is not prime, then eventually we decide that the number is prime. And this figure here shows different values of RSA, so RSA 100. This here, this entire thing here is a single prime number. And for RSA 2048, the modulus, or n, has 617 decimal digits, and this entire thing here is one number. Okay, so this shows you how big a number should be for the algorithm to be secure. This is actually why brute force is nearly impossible in this case. The number is just too large. And this is why doing operations on RSA is mathematically challenging. This is why we still use AES, because it can actually achieve high security with a much smaller size of key. Okay, we saw the square and multiply algorithm. For choosing the value of E, obviously it has to be relatively prime to phi n. And so typically we choose prime numbers. But again, if you choose a small value of E, the algorithm will be faster, but it will be less secure. So one value of E that is actually very popular is 65,537. It's a prime number. You can actually, I don't actually know if it's a prime number or not, but it is a number that is used a lot. Okay, how do we break RSA? As we know, the approach to breaking any algorithm is either the brute force attack or a cryptanalysis attack. And in public key cryptography, we said that brute force is infeasible because of the size of the key. And so we go for cryptanalysis attack. There are two popular ones. First one that I will discuss is called the timing attack. Basically, when you do an operation, a mathematical operation on RSA, the result of the operation depends on the size of the number. So a timing attack will observe how much time it took for encryption and decryption and will guess the size of the number based on that. If you're trying to encrypt a large number, it will take you more time than if you encrypt a small number. And so this is what a timing attack does in order to narrow down the search space as to which numbers should be tried out. However, the more popular attacks on RSA are mathematical in nature. And the most well-known attack is the factorization attack. Basically, if you want to obtain the private key D, you have to use this equation. ED mod phi n is equal to 1. E is known. Okay? E is known. E is the public key. But nothing else in this equation is known. Remember, you don't know phi n. You know n. Okay? You know n, you don't know D, and you don't know phi n. So the factorization attack allows you or goes into obtaining phi n given n. How will you obtain phi n given n? Phi n is actually equal to p minus 1 multiplied by q minus 1. So in order to obtain phi n from n, you have to obtain the values of p and q. This is actually why it is called the factorization attack. The factorization attack goes into factorizing n into the values of p and q. If you are able to factorize n into the values of p and q, then you will be able to know phi n. And so you will have now an equation with only one unknown, which is d. Then you can use the Euclidean algorithm to obtain it. This is actually the entire thing. This is the well-known attack on RSA. Everyone knows it. The problem is if you want to factorize phi n, if you want to factorize n, sorry, you have to factorize something that looks like that. You have to factorize the number that has 617 decimal digits. It's not a feasible attack. It's a very, very difficult one if the numbers that you chose are large enough. Everyone knows it. It is indeed difficult to execute. Last thing we will discuss today is what is called the Euclidean algorithm. And basically, we have been saying that if you have E and you have phi n, you should be able to obtain D using the Euclidean algorithm by solving this equation. Now, I will actually show you two examples of how to do that. So the first example says, given E and n is equal to 5 and 851, so E is equal to 5 and n is equal to 851, obtain D. Okay, so we want to be able to solve ED mod phi n is equal to 1, and we don't have phi n. That's the first thing. You have to factorize. Okay, you have to factorize n. So n is the product of two prime numbers p and q. So the first thing you do is you try different prime numbers. If the number is small enough, then there is not actually going to be a large number of prime numbers to try. If you factorize 851, you will get actually that the only two prime numbers that fit are 25 multiplied by 37. Okay, so now you have P and Q. Now you can calculate phi of 851 to be equal to 24 multiplied by 36, P minus 1 multiplied by Q minus 1, and you will get sorry, this is 23 multiplied by 37. 851 is 23 multiplied by 37. And so phi of 851 is actually 22 multiplied by 36, which is equal to 792. Okay, now you have phi n. Now you can solve ED mod phi n is equal to 1. How do we do that? We rewrite as 5x plus 792y is equal to 1. This is actually the Euclidean algorithm. We want to find values of x and y that fit this equation. If we do find values of x and y that fit this equation, then x will be D. X will be the private key. How do we do that? First of all, we divide 792 over 5. Okay, so 792 over 5 will give you 158, 158.4. Okay, so 792 minus 158. Okay, so just actually take the floor of this number, 158, 158 multiplied by 5. That is equal to 158 multiplied by 5 is equal to 790. So you take 792, okay, which is phi n, multiplied by 158 multiplied by 5. Okay, that will give you 790. So the subtraction will be equal to 2. I'm just showing you the steps, and I'll show you how it will make sense. Basically, what we're trying to do is that we're trying to rewrite this equation such that we figure out the values of x and y. So the first step is divide 792 by 5. Okay, you will get a number, which is in this case 158.4. Take the floor of this number, which is 158, multiplied by 5. You will get 790. 792 minus 158 by 5, or 790, is equal to 2. Okay. Now, you try and rewrite. Ask yourself 5 minus the result of this subtraction, which is 2, multiplied by what, such that you will get 1. Okay. Why are we doing that? So that these two equations now become similar. So obviously 5 minus 2 multiplied by 2 is equal to 1. Now, take a look at this equation and compare it with this equation. Okay, it's not yet very similar. What if we replace 2 with this equation? Because this equation is actually equal to 2. So 5 minus 2 multiplied by 792 minus 158 multiplied by 5 is now equal to 1. Okay, so group all the 5s together and put everything on the other side. So 5 multiplied by 1 plus 10, sorry, plus 2 by 158 plus 5 multiplied by 5 minus 2 multiplied by 792 is equal to 1. Okay, if you do this addition multiplication, you will get actually 5 multiplied by 317 minus 2 multiplied by 792 is equal to 1. Now compare this equation with this, with this equation, and you will get that x is equal to 317. Okay, that's actually our goal. We want to write an equation, which is this one, that is similar to 5x plus 792 is equal to 1. Okay, let's go over this example again. Basically, we started with n. We factorized n. N is equal to 851. We factorized it into p and q, which is 23 multiplied by 37. From that, we calculated phi n, which is 22 multiplied by 36, or 792. And then we wrote this equation, 5x plus 792 is equal to 1. Okay, and then we started to try and rewrite this equation such that we figure out the values of x and y. First, we divided 792 by 5. You get obviously a number that is not an integer, so you get 158 by 4. Take 158 and multiply it by 5. This is 790. So 792 minus 158 by 5 is equal to 2. 792 minus 790 is equal to 2. And then you write this equation. You take 5 and you ask yourself, 5 minus this remainder 2. The result of this subtraction 2 multiplied by what will give us 1. So 5 minus 2 multiplied by 2 will give you 1. And so take one of these two 2's and replace it by this equation. So 5 minus 2 multiplied by 792 minus 158 multiplied by 5, this will actually be equal to 1. Take all the 5's and group them together. So you have 1 5 here, and you have 158 multiplied by 2 5's there. This is actually equal to 317. So 5 multiplied by 317 minus 2 multiplied by 792 equal to 1. And now x is equal to 317, and you have obtained the private key. Okay, let's take another example. Given E and N is equal to 7 and 247, obtain D. So N is equal to PQ is equal to 247. If you factorize that, you will actually get 247 is equal to 13 multiplied by 19. So you got P and Q out of that. This means that phi of 247 is equal to 12 multiplied by 18, which is equal to 216. Now we're ready to write our equation. 7 plus, 7x plus 216y is equal to 1. This is actually what we are trying to solve, 7x plus 216y. So as usual, what do we do? First, we divide 216 over 7. Okay, so 216 divided 7 will get you 30.8 something. We don't care about what is the rest. So now 30 by 7 is equal to 210. Okay, now we can say 216 minus 30 by 7, okay, is equal to 6. 216 minus 30 by 7. This actually came from this equation. You divide 216 over 7, you get 30 point something. Take the floor, which is 30, multiplied by 7, you get 210. And so 216 minus 210, which is 30 by 7, is equal to 6. Now you ask yourself, 7 minus 6 multiplied by what is equal to 1? Okay, 6 is the result of the subtraction. We want to figure out a number such that when we multiply it by 6 and subtract this result from 7, you will get 1. Obviously, the result is 7 minus 6 multiplied by 1 is equal to 1. And now, in this equation, take this 6 and replace it by this equation. So 7 minus 216 minus 30 by 7 is equal to 1. And so group all the 7s together. So you have 7 multiplied by 1 plus 30 by 7 minus 216 is equal to 1. So now you have 31 by 7 minus 216 is equal to 1. Okay, and now you can say that x is equal to 7. Sorry, x is equal to 31. Okay. All right. That's it for this lecture. You will see other examples about the Euclidean algorithm in the tutorials. The only way to study RSA is to work by hand. Try to do some of the encryptions and decryption, try to do the Euclidean algorithm, and try to do the mathematical proof of RSA by yourself. And I will be talking to you next time.